Welcome everybody, I'm Jolene Moon and you've landed on my Science is Magic YouTube page where I talk about the science and maths that fascinates me. This is going to be the first physics video of the GCSE Minecraft and Chill revision series where we're going to casually chat about the stuff you need to know for your physics exam, and I'm going to entertain myself and possibly you with some Minecraft shenanigans at the same time. So grab a cup of tea, do whatever you've got to do, and maybe you'll absorb some revision advice at the same time. Today's videos have a theme of FAQs and revision tips and exam strategies for summer 2024. So what we're going to do is try and get to my new End Gateway portal. I did see that I'm looking in completely the wrong direction and making Endermen very angry at me. Why don't I just go ahead and get on with the first FAQ. My first physics FAQ is, why is physics so boring? Physics is so boring, and to that I say, how dare you? But also I get it. There we go, there it is. I also, controversially perhaps, as a physics PhD student now, found physics to be the most boring of the three sciences, physics, chemistry, biology, at GCSE, and I don't really understand how now that was the case, because how could I possibly find how the universe works boring? It's not boring. It's to do with how it ends up being taught in classrooms. In a classroom scenario, teachers have limited time, limited resources. They've got to focus on what's on the syllabus, and that isn't a very interesting amount of physics, because there's a few different reasons why you might be learning things on the physics syllabus, and none of them are because it's interesting, because it's a fun thing to know these things. That's just not how that works. But I'm just going to concentrate and look for the number here. I want to go to 28 and 27, or should go 28 and 29. Let's do that. Already getting distracted. I was terrible in the last video. So in my last video, where I talked about maths FAQs, I fought the Ender Dragon, because I'm looking to get all of my end gateways sorted out on my survival world here. But I'll go back to talking about physics now. So physics in the modern curriculum is not as exciting as physics used to be. People who studied physics in the past were witches, they were wizards, they were medicine people, they were healers. They were very important, particularly astronomers, because we needed to know how the land worked. We needed to know how the seasons were going to change, and our place in the heavens, in the sky. They were masters of the craft. They became the engineers that started to advance humanity to the hellscape dystopia that it is now. But the way that they did that, and we can all do that, we can all have that level of understanding of the earth around us, and it's really that understanding of the earth around us that gains us mastery of the craft, right? And we can then start to manipulate the world around us to do things like build bridges and understand what funny looking shiny rocks in the earth will turn into these substances with incredible properties that go into our smartphones. Shout out to the Democratic Republic of Congo. So the way that we start to understand those materials is through the scientific method, or that's how scientists in the global north and global west have decided is the best way to do that. And the scientific method came from Islamic scholars from the north of Africa and southwest of Asia, prior to the Greeks and Romans, who then took it and ran with it, so to speak. And the scientific method is the way that we, it's not the only way that we can do things, but it is a very good way for achieving the precise mechanical understanding of the things that we have evidence for and what we see in the world. And we gain a very specific perspective of what to do with everything, I suppose. We gain the knowledge of what we see in front of us is what's real, and how can we change that so that we can see other things that are real, so we can call to life things like a bridge, and that can get boring if you're learning it for the first time, if you've got to start with the basics. Obviously, when you start to learn the fundamentals of forces, that's not quite as exciting as here's these resources, let's go build a bridge, or here's this funny little box with some little sensors and an electric circuit inside. Let's see how many cavities and caves are in the ground underneath our feet. Like, physics starts to get incredibly exciting at the later levels that you study it, at the higher levels that you study it, but unfortunately you do have to build that foundation of knowledge first before you can get to a point of mastery, and that can be a little bit of a grind. The early levels aren't as exciting as the higher levels, we all know that. But anyway, on to the next. So the next FAQ that I get is where is my stone? That's not the FAQ. The next FAQ is electricity. Nobody understands electricity. I get asked all the time what is going on with this topic, electricity, and they just don't understand it, don't understand what all the symbols mean, don't understand what's going on. And to that I say that you're not alone, first of all, because like I said, I get asked this by everybody all the time. So I'll just give a little bit of a sort of what I would say if we were in a lesson and my student said, I really don't understand electricity, please can you help me? I would say to that, yeah, sure, okay, let's do it. Question to you is, do you understand what electricity is? Because if you can't tell me what electricity is, how can you expect yourself to understand the topic or build on that knowledge, to learn what you need to know about electricity as we develop that understanding and then get to some higher concepts with it. And of course all the little symbols are that's a case of memorization. There's not really a lot we can do with that. And most people don't really know what electricity is, so when they answer my answering their question with a question, they come back to me with, oh, electrons. It's something to do with these little particles called electrons. And yes, you're right. But let me give you a little bit of background context. So we have something called the standard model in physics. Don't panic. I'm going to take you through it. We're not going to learn the standard model. Think of it like the 4 elements: water, earth, air, fire. But in the standard model of physics, we have strong, weak, electromagnetic, and gravity. And that might seem like an odd combination of fundamental forces at first. But when you start to develop, if you do A-level physics or if you take your physics understanding beyond this point, that will make a lot more sense. Now, the strong and weak forces, don't worry about those. What's more interesting at this level that you're at is the electromagnetic force and the gravitational force, obviously. Now I'm going to put myself on toggle so I don't fall off while I'm chatting to you guys. Right, there we go. So what you'll notice first of all straight away is that electricity and magnetism are combined into one force, the electromagnetic force. And that's interesting, and if you've never considered why that is or what's going on there, you might be confused, quite rightly. and that's because they are acting on the same particles. Both electricity and magnetism are forces that are carried by the particles called photons, which you can just think of as light, particles that carry light, and that's why we often talk about the electromagnetic spectrum of waves of light frequency, and both these photon-carried phenomena act on the same particle, electrons. So what I want you to think of is electricity and magnetism as kind of the x and y axes of one particular type of force. So in the same way that you can grasp the concept of gravity acting vertically, or sort of it's unidirectionally from a central mass, right? But on the averaged out flat surface, we understand that gravity acts vertically down towards the center of the Earth, and from there you can build that understanding into applying it somewhere else, i.e. electricity and magnetism, and consider that electricity is, for example, instead of just vertically, we have an x-axis of electricity and a y-axis of magnetism. And it's true actually that they, when we consider them as forces, as vectors, that they act perpendicular to one another. So that's quite a handy analogy. So just as you understand, gravity acts in 3D, but primarily vertically. So we've got an x and a y-axis here, and I'm just demonstrating that on the screen. Well, it's x and z because y is the vertical, but as long as it's an orthogonal or perpendicular axis, it doesn't matter what we label them. So just think of electricity acts in the north-south direction, whereas magnetism acts in the east-west direction, and that's acting on the same particle. Doesn't matter which way round. So if you understand that that's what electricity is, and that's what electricity is doing, it's just one component of this two-directional phenomenon, you can think about what phenomena might arise from that. And you'll start to understand electricity a lot better if you get that. I'll go into more depth and more explanation on that another time. For now, we'll keep it moving. So I just mentioned then vectors and scalars, which is the next FAQ that I get. So I don't understand the difference. What is the difference between vectors and scalars? Well, my friend, I can tell you. The difference is kind of what I was just talking about with direction. So it's all about direction and quantity. So when we're talking about vectors and scalars, we're more often than not talking about forces. And the thing about forces, oh, I did not want to do that. That's incredibly annoying. Oh, we got it. Awesome. With forces, what are we doing when we're studying forces? We're looking at the direction that something is happening, right? We're looking at some kind of result from some kind of action, and we care about the direction that happened in. The direction matters when we're studying forces. And what arises from that is that we notice that there are certain actions that result in an effect in all directions, certain actions that result in an effect specifically in one direction, and certain actions that will have an effect in no directions. Now that sounds a bit bizarre when I say it like that. I say it like that to get the point across that consider time as the first example. This is where we start. Time has one direction, it has a fixed direction, forwards. Unfortunately, as of yet with our technology, going backwards in time is not generally available to the public, right? So we are going forwards in time. So time is a scalar because it doesn't have a necessity within that quantity to specify a direction. right? Does that make sense? So a vector is a quantity where you have to specify the direction that the action is taking place. So if someone pushes you, you inevitably will care about the direction that that happened in, right? Because if they push you forwards, you're going to land on your face. And if they push you backwards, you're hopefully going to land on your butt and not damage anything. Whereas if you are being pushed sideways and you happen to be at the edge of a cliff, that's a much less preferable direction, right? So the result of an action, the direction matters when it's a vector, and all forces are vectors because we, like I said, care about the direction that they happen in regardless. But time is a scalar because that's just a quantity, but I think the just a quantity explanation for scalars isn't really helpful if you don't understand what we mean by that. So I tend to think of vectors as a quantity where we have to specify the direction because we don't necessarily know it, and it could be any direction. Scalars are quantities where they have either a fixed direction, they happen in every direction, or they have no direction associated with them. So time is the example where it goes only in one direction, it's fixed, it goes forwards. But energy is a quantity that it has universal direction. It goes in all the directions. Let me just check. Yeah, okay, I'm fine. Let me think of another one. Speed. So speed is the quantity that describes how fast someone is moving. That has no direction. We can change speed into a vector and call it velocity, and that tells you how fast someone is going in a specific direction. I just made an Enderman mad. That's bad. He's going to come and push me. Yeah, let's get away from the word there. Velocity is the vector version of speed because we specify the direction that something or someone is going in, and how fast they're going in. But speed itself is just the quantity that describes how fast, right? Velocity is how fast and in what direction, but not all quantities, not all scalars have a vector equivalent, only some of them do. So like energy, for example, has energy just spreads out in all directions, right? Not really much we can do with that, but momentum is sort of the direction that energy is carried in. Not quite, don't take that as gospel, but not all scalars have translatable equivalents in vector form. And here's an example of, so time has a fixed direction. Speed is something where we can specify a direction, but it doesn't inherently have one. Energy goes in all directions, can have related quantities with specific energy being carried in certain directions. And here's one with no direction, volume. The volume of an object, how much space it takes up, is just a quantity. It's not, I mean, you can consider the center of gravity, and then you're talking about forces again, to have a direction that's sort of related to the volume, but just the volume itself, how much space it takes up, no direction associated. So volume is a scalar. Same thing with area, length, those kinds of dimensions, they are all scalar. Because they have no direction associated with them, and they can't have a direction associated with them. They are just quantities, they are just measurements of something. So I hope that makes sense. I hope that clears that up. Again, I will be doing a more in-depth chat about the forces topic in physics, so we will get to discuss that in some more detail another time. But I think it's high time I get on to some revision tips before the end of this video. And my biggest revision tip for physics, especially given my first FAQ, is that I would highly recommend everyone get interested, find out which area of physics interests you, even if that's only vaguely, even if that's not really interested in it, but this'll do, this is enough to keep me reading about it. and then do that, and then read around it. If you can get to a point in your physics study where you're enjoying reading about a particular topic, and for a lot of people that's space. People love reading about space. Some people love reading about the fundamental nature of matter and energy in the universe, and that's, that's physics, the whole jam with physics. So if that interests you, read about it. Physics is not just for the witches and wizards. Anyone can read about physics if it's interesting to them. Don't feel held back by any notions about who physics is or isn't for. And get yourself into the library, get a book about that topic in physics, no matter what it is. If you're interested in light, if you're interested in lasers, get something related to lasers. If you're interested in, so for me, I didn't realize, and I'll be talking about this next week actually, with the next themed set of videos. I had no idea that X-rays were used to study crystals until I got to university, and suddenly I was interested in the electromagnetic spectrum and how light works, whereas I had never been interested in that at school. So you never know, there might be something. Now, the other thing I would say is when you're reading around it, don't be intimidated by not understanding everything. You don't have to understand it all to be interested in it, right? And if you don't understand something and it's not necessarily within your GCSE syllabus, that's fine. You can always ask a teacher or a tutor, or drop it here in the comments if you want to understand it. But most books, if they're written in an accessible way, will be written so that you can kind of get to grips with it. And there are lots of famous and popular science writers who do that job for you, so that you're always going to be able to find some material to read about the topic in physics which interests you. And if you don't know what that is, think back to any lesson. If there was any lesson where you weren't completely switched off, and you found something even vaguely interesting, that's the one, right? And just start there. Or think about, alternatively, your interests. What are you interested in? And think about how science and physics relate to that. Because they do, in some way, they're related to everything. So maybe that's a good place to start for you. If you think, oh, there's absolutely nothing here that would possibly interest me, I would challenge that. I bet there's something. All right, next tip. The fundamental patterns underlying everything in physics, that is something to look for. So I had a fantastic set of teachers in my school, in my GCSEs particularly, and my A-levels. And one of the best things my A-level teacher said to me, shout out Mr. Maybe, he was literally called Mr. Maybe, and he hated the song Call Me Maybe. Anyway, just flashbacks to people making fun of the physics teacher. The physics is like a puzzle, a big jigsaw puzzle, and you've got to fill in with your education all the different pieces. And if you can see it like that, as it's just a pattern of different pieces of knowledge that eventually build together to make some kind of coherent story, that will, if you watched my last video on maths and studying maths and my tips for that, you'll know that I said about knowledge bridges. And I warned you I would talk about this all the time, and I do. My steering is gone out. Okay, let's use some practicing. The fundamental picture of physics, that's what physicists are looking for, is some kind of unified theory to explain everything. And with your education, you do learn a pretty coherent story. So if you can see how that all fits together, how do all the topics relate to one another? What are the patterns that connect them? see it all as the same set of fundamental, that's why they're called the laws of physics, the same set of laws that are describing everything that you learn about. And you'll start to find things easier to remember and understand if you can do that. Now, my next tip is when you're repeating practice questions and doing loads of practice questions, that's great, that's fine and everything. But if you can, I'm going to take NCM with me. If you can, see what the invisible, so in my last video I talked about exam language and clues, and in physics you've got to put your detective hat on and look for clues in the question for what topic they're asking you about, because they're not trying to trick you, they are looking for specific answers that relate to the topics that you've learned about. But it can be tricky, they kind of obfuscate it in certain ways. So look for the clues, see the invisible question that's actually being asked, because if they just said repeat and write down the definition that you learned for this thing, of course you would know what they were asking for, that would be easy, but they're trying to get you to, this is when I was talking about lateral thinking last time, they'll try to get you to sort of think about the problem and connect and make associations. This is why learning the patterns is my best tip for your revision. And then see if you have a little bit more success with practice questions doing it that way. And my last tip is don't try to grasp everything all at once. Don't try and get all of the complicated concepts and ideas straight away. Kind of similar to a tip I gave in my maths video, is that you wouldn't expect yourself with a physical exercise to be able to do the most complicated and convoluted thing right away. You've got to start small, start with the fundamentals, and then you can build on that later. So start with whatever the headline or key idea is going to be for that given topic, and then you'll be able to build on that much more easily. So when you're going through your notes, when you're reading through your revision notes, think, what is the headline? If this topic had a headline, what would that headline be? If it had a subtitle, what would that subtitle be? Is it a key equation? Is it a key definition? Is that just a key, like a piece of understanding? What am I missing? What's the fundamental thing here that I need to grasp? And then you'll be able to, that will improve upon the last tip, which is be a detective, understand what is going on with your exam questions. Now I'm fully stranded, aren't I? I'm trying to figure out which of these islands is the closest. It's probably that one over there. I'm just going to end up having to bridge to another. Alright, that's what the end is all about, isn't it? Just make sure that I am on shift. Would have been funny if I wasn't, wouldn't it? Okay, I'd have one more tip that I've just thought of. So I said that was the last tip, and then I'll carry on talking at you. But it kind of relates to the last two. It's not really new, and that's when you're learning and you're thinking, what's the headline of this? If you understand what the headline is and you've got to grips with the basics, and you're getting better at getting your detective hat on in the exam, and asking yourself, why am I learning this? Right, that's when you go from being a detective to being the inspector or the investigator, right? So you've got to figure out what are they asking me, and then why are they asking me about this? Why did you even have to learn this in the first place? Was it because of just improving your worldly knowledge about a phenomenon like gravity? Was it to give you foundational knowledge to build on for further study in that subject, which is kind of what I feel like studying light and the waves is all about? Is it to improve my knowledge and skills if I go into a certain part of the workforce? I feel like that's what some of the electricity and forces are about, if you want to become an electrician or an engineer or something. And then beyond that, is it about just general, like I said, general worldly knowledge and safety? Is it about teaching me something that will be important? And so part of our everyday life in the UK is using electricity and understanding the national grid, and that's why you have to learn about it and understanding where our sources of energy come from. So I think that wraps me up here. I will just keep bridging. I'm pretty stranded out here, it seems, with no city in sight. But I will, and I don't have any stairs to get down either, so I think I'm going to have to chuck a pearl when I get overland there. But anyway, I hope this video was helpful. Thank you for watching all the way to the end. Let me know if you want me to keep chatting like this and revising with you. Like I said in my last video, we are going to get to more specifics in the topics eventually. Don't forget to check out my other videos. We've got a maths one and a chemistry one for today, talking about also very, very chatty FAQs and revision tips, and making your plans and strategies for your revision leading up to the summer exams this year. Don't forget to be kind to yourself. Our words are spells. Live your best magical life, and I will see you next time. Yalla, bye.